Okay, so we can officially start the meeting. So hello everyone, and then thank you, especially Alex, for your talk. And just to give you to all of us intro, so actually Alex is a PhD student at the AutoML Freiburg Lab, and where he is supervised by Professor Frank Hutter. Is it, I think, the right name right way to pronounce the name? And currently, research focus of Alex is about tabular foundation models and especially how to extend them to the textual modality. And also, Alex is for a longer time in Freiburg. He also finished his master's degree at the University of Freiburg, and currently he's here focused primarily on tabular foundation models. And also, the talk is on nanoTabPFN, which is a research, I would say, version, a small version of famous TabPFN that also enables us researchers to, I think, just learn more about how the model is built, what is the architecture, how we train these models. So with that, Alex, the floor is yours, and thank you for your presentation.
Okay, thank you. So my talk is about nanoTabPFN, a lightweight and educational reimplementation of TabPFN. So why do we want something like nanoTabPFN? Well, TabPFN is the state of the art in tabular foundation models, especially its newer versions. And back then, when TabPFN v2 was released, it was a Nature publication and also state of the art. But the problem is that it's hard to understand, modify, and play around with, since the code base was over 10,000 lines of code back then. And we wanted to have something akin to NanoGPT for the tabular foundation model world, because we saw that NanoGPT enabled a lot of students to learn about GPT. A lot of researchers also tried different methods on there, and we wanted to enable the same for TabPFN. So I roughly structure the talk like this. First, I will talk about TabPFN in general on a high level. Then I will give an introduction to nanoTabPFN and the specifics in there. And afterwards, I will talk or mention multiple works from our lab that build upon nanoTabPFN. So what is TabPFN? TabPFN is a tabular foundation model. And my mental model that I would recommend for you to think about it, in case you know about LLMs, is essentially that it's somewhat similar to an LM, as in it's a pre-trained transformer, but it is different in what the architecture is and the input and the output. In the LM world, you have a prompt as an input, you have your pre-trained foundation model, and then you get some output. And in TabPFN, you have a table as input. To be exact, we have the X-train and Y-train, so the training part, as well as X-test, the features of the test data points as input. That's essentially the prompt. Then we give this to our model where we don't change any weights. It just does a single forward pass, and this will give us the predictions for Y-test. Now, what is different between TabPFN and some LLM is also two things. The architecture. In LMs, we have like a 1D attention across like the words of a sentence. And in TabPFN, we inherently have a 2D architecture where we have multiple rows and columns. And so you will also see a corresponding change in the architecture later. And another important point is that TabPFN is a prior data-fitted network, which means it was trained purely on synthetic data. So we have some method to synthetically generate millions of synthetic data sets, and we use these for pre-training. A high-level illustration of the training here is this here. So we have some method, the prior, which you can think of as something that generates realistically looking tabular data. And from this method, we generate millions upon millions of data sets. For TabPFN v2, this was 130 million. Now in this visualization, we just have 1D data sets, but in the actual TabPFN v2, this was very high dimensional data. You can think of like 100, 200 features or something. Now, once we have these data sets, what we can do is we can create a train and test split inside these. This is indicated here with the blue and the orange dot. And then we can take one of these data sets, give it to our transformer architecture, and ask it, given the training data points, here visualized in blue, and given the feature of X test, here visualized in yellow, what is the actual Y value here? And our architecture will give us some probability distribution as output. And then, since we synthetically generate the data, we can compare this to our ground truth. And based on this, compute the cross entropy, backprop, and improve our foundation model. Now, how do we generate the data that we use? There are different methods. I will talk about the SCM, structural causal model prior, and about the MLP prior in a bit. Now, the idea of the SCM prior is that we generate a graph, we generate connections inside this graph, and then we assign certain nodes in the graph as features and as target and as labels. So in this visualization, we have x1 as a feature, x2 as a feature, and this node here is the label. And then we have certain nodes which we define as input. Then we go and we instantiate certain weights for that graph, for the connections. And then what we can do is, okay, this shouldn't come slowly. I didn't have the time to adjust the slides here. But the idea is essentially we generate a random graph, we generate certain weights on the edges, and we assign the nodes as variables, as features, and as targets. And what we can then do is we can generate random noise at the noise values here, for example, epsilon1, epsilon2. Then, once we have those, we can propagate the values throughout the graph. For example, when we start with 0.7 for epsilon1 here, we have an edge with 0.5. So we multiply these two values, and this will give us 0.35 at this next node here. And we just keep propagating throughout the graph to actually compute the values. And once we have the values computed for each node, we can then look at which nodes were the features and the target, in this case x1 and x2 here. So we know the features would be 0.33 and 0.35, and the target would be 0.35. And we sample one graph, we then sample differently randomly generated data. So one time we generate 0.7 and minus 0.3 as the noise. The next time we generate 0.1 and minus 0.2 as the noise. And the next time we generate another noise as input. We then propagate this throughout the graph, and then we record the values at the features and the target label. And once we have this, we essentially get the pair of a single data point. And once we have those, we essentially have now 3 rows in our tabular data set. So one graph essentially describes one table, and by propagating different random noise throughout the same graph, we can get different data points for the table. Now, if you want to do classification, then we would want to threshold the label here at a certain value, and then we can, for example, have a binary classification task instead of regression. That's the SCM prior on a high level. I will mention it later again. Now, one principle we follow in TabPFN is the simplicity principle. So more complex SCMs, which describe more complex functions, are less likely to be sampled during our pre-training, and simpler SCMs are more likely to be sampled. It's like akin to Occam's razor. If there's an easier explanation, we should follow the easier explanation. Now, another prior, which might be a bit simpler to explain on a high level, is the MLP prior. You probably heard before that MLPs are universal function approximators. And so you can think that if you take a random MLP with random weights, this essentially describes one arbitrary function mapping the input features x to the label y. And we can leverage this in order to generate tables by sampling a random MLP architecture, which means the depth, the number of hidden nodes, and activations. Then, once we have the architecture defined, we can sample random weights for this architecture. Now we essentially have multiple n.linear layers instantiated with some activation function between them. And then this essentially defines one table. And in order to generate data points of the table, we can sample random features x, and then give them as input to the table, give them as input to the MLP, propagate it throughout the MLP, and get a label as output. And this essentially defines how we get one XY target pair of our table, And if you generate other random features and propagate them through the same MLP, you get another data point of the same table. So on a high level, these are like different methods that like you can use to describe functions, and thus you can also use them to generate tables. Now, when we look at TabPFN, there have been 3 different major versions. The first one was released in 2022. This did attention across row embeddings. So it embedded full rows, and once you had an embedding, we just applied a transformer one-dimensionally across these. Now, TabPFN v2 was released last year, and this is also what we based nanoTabPFN upon. There, we had alternating attention between the rows and the columns of a table. And so there we operated on embeddings of single cells, not rows. Now in TabPFN v3, which was released very recently, we first embed the cells in a column-wise manner, so they attend to the other entries in the same column in order to compute their embedding. And then once we have that, we do row-wise aggregation, and this gives us a row embedding, and there we do, like in TabPFN v1, a one-dimensional attention again. And this was inspired by Tabical, which is another competitor to TabPFN, which is also a tabular foundation model. Now, when we look at the results on TabArena, we can see that TabPFN v3 is dominating it here, and its previous versions, like the real data fine-tune of TabPFN 2.5 or TabPFN 2.6, are closely behind, followed by Tabical, which is also another tabular foundation model. And once TabPFN v2 was released, back in the day, it was also the state of the art back then. Here we are looking at small data only, because TabPFN v2 had certain limits on the size of the data. But if you look at the full list of TabArena datasets, TabPFN v3 is also state of the art there. But due to the size limitations, TabPFN v2 is a bit lower. So this was the high-level idea of TabPFN. Let's go into nanoTabPFN. So nanoTabPFN is essentially to TabPFN v2 what nanoGPT is to GPT-2. It's a lightweight educational reimplementation, and we created this originally for teaching about TabPFN at our university. And then we thought, how could we maybe make a workshop paper out of this? So we made some experiment on pre-training very fast on very small data, and submitted this to the AI for Tabular Data workshop at Europe's, where it got accepted as an oral. And you can check it out under this GitHub repository. If you just Google nanoTabPFN, you should be able to find it. And here's a very small code example where you can see like the simplicity of it. We essentially have 2 files, a model file and a train file. All in all, these files are below 500 lines of code, and you can just instantiate a model, instantiate a data loader for the prior. We provide a set of pre-generated tables here, which you can use. And then you can just call the training loop to train it. So what's the difference between TabPFN v2 and nanoTabPFN? Well, TabPFN v2 had a very large code base of over 10,000 lines and included a bunch of features, for example, KV caching, which make the code much more complex. And in particular, we decided that there are some features which we deemed non-essential. And so we removed these in nanoTabPFN. This drastically reduced the size of the code to less than 500 lines. And we also decided that we wanted to have an experiment with pre-training. And so we did one where we trained a much smaller version. So not only did we reduce the size of the code, but we also made the model smaller that we instantiated for our experiment. And this reduced the size by a factor of 20. And when we look at the pre-training time, this reduced the pre-training time from over 2 weeks on 8 GPUs to 1 minute on 1 GPU. But you need to keep in mind, this is on very small data only. So if you train on very small data that fast, then you evaluate on full TabArena with 1,000 data points and 100 features, this will not look competitive at all. Now let's look at the architecture. On a high level, the architecture consists of 4 different parts: the feature encoder, the target encoder, the transformer block, and the decoder. The feature encoder takes the X matrix, like the feature columns, as input. It then normalizes per column, and afterwards it embeds the cells of the table. It embeds these independently of each other, and it applies the same linear layer, mapping from a scalar value to a high-dimensional embedding. The target encoder does something very similar. It takes ytrain, then it pads this up to the length of ytrain and ytest by imputing ytest with the mean across ytrain, and then it uses a separate linear layer to map from a scalar value to a high-dimensional embedding. We do this because we need the high-dimensional embeddings so that we can do our alternating attention on it. Now, the next step is this transformer block. Here, this consists of the alternating attention with the feature attention in the beginning, the sample attention afterwards, then followed by an MLP. In the feature attention, all the cells inside one row attend to each other. And in the sample attention, all the cells inside one column attend to each other. But there's a small change inside the sample attention where we make sure that the embeddings of ytest, that the embeddings of the test data points do not attend to each other, and they do not attend to the training data. We do this since we don't want the predictions for test data point to change if we add another new test data point. And we don't want to do transductive learning. Now, after applying this alternating attention, we have an MLP. This then concludes one transformer block, and this transformer block is repeated multiple times. And afterwards, we take our embeddings and we apply a decoder. This decoder takes the embeddings of ytest and maps them to a probability distribution. And this decoder is essentially just a two-layer MLP. Now, one small detail inside this transformer block, which I couldn't visualize here nicely, is that we have residual connections around the attention blocks, and we use a layer norm. Now, when we look at what's different between TabPFN v2 and nanoTabPFN, well, the first point is feature pairing. So in nanoTabPFN, like I mentioned, cells are embedded independently of each other, whereas in TabPFN v2, pairs of cells are embedded together. And this makes it just like more complex to think about this, since you don't have one embedding for each cell in the original table, but you have like half the number of embeddings. And this can help, I think, with like certain kinds of data sets. I think in the technical paper, they had an experiment where they showed that this and positional encoding can help with representation collapse. And in general, this seems to improve performance by a few percentage points. But we deemed this not to be like an essential part of the architecture, and for simplicity reasons, kept that out. Similarly, TabPFN v2 adds a column of like hash values, which is supposed to help distinguish two rows which otherwise have the exact same features. We also remove that. And then for missing values in categoricals, in nanoTabPFN, you need to pre-process them by imputing or ordinarily encoding them. In TabPFN v2, missing values were handled inherently. And lastly, when it comes to TabPFN v2, if you call .fit and .predict, you don't just do a single forward pass throughout your PyTorch model, but instead you do actually 4 separate forward passes and then average the predictions of these. Whereas in nanoTabPFN, one .fit .predict call is just a single forward pass, and that's it. So in the workshop paper, we had a small experiment where we pre-trained on small data with like 150 data points, 5 features, and we evaluated on slightly larger data, like 200 data points, 10 features, and we looked at the performance over its pre-training time. And we were able to see that nanoTabPFN reaches random forest performance within a minute, and shortly thereafter, it also surpasses TabPFN v2 without this ensampling of preprocessing, and also gets somewhat close to TabPFN v2 with the ensampling of preprocessing. But keep in mind, this is on small data in particular. If you would use the TabPFN v2 architecture and you only pre-train it on small data, I would also expect this to be better than nanoTabPFN. Now I will talk about some work that we did that builds upon nanoTabPFN. I will not go into that much detail for some of them, but I will give you like a high-level idea. The first is speedrunning tabular foundation model pre-training. Here, the idea is that there is this modded nanoGPT repository which emerged from nanoGPT, and people build a community around speedrunning the pre-training of nanoGPT. And this reduced the pre-training time from 45 minutes to just 80 seconds. And we wanted to do the same for TabPFN. So as you can see, we had GPT-2, then Andrew Karpathy made nanoGPT, and then Jordan Keller made modded nanoGPT. Here we had TabPFN v2. Me and my co-authors made nanoTabPFN, and then a student of mine, Salih Bora Öztürk, made modded nanoTabPFN. Now you might think that in nanoTabPFN we already pre-trained fast. So isn't this already winning the speed run? Well, there's a difference. In nanoTabPFN, we focused on very small data, and we cared about having ultra simple and small code. Whereas in modded nanoTabPFN, we scale up the evaluation data to 1000 data points and 100 features, and the pre-training data, and we also scale up the architecture. And in modded nanoTabPFN, we are open to try much more complex engineering tricks, which make the code harder to understand, because we just care about improving the speed run, and we don't care about like it being readable or lightweight. Now, the rules, we don't have to go into detail, but we are essentially still trying to beat random forest on a bit scaled up data. We only measure the training time, so we don't measure the evaluation time, and also not the data generation. And we fix the hardware to one L40S GPU. If someone wanted to submit their code and didn't have a GPU, my student would run it and report back the results. Now, the results of the speedrun were that we reduced the pre-training time from 74 minutes down to less than a minute, and the number of data sets from over 80K down to below 4K. And we had a bunch of hyperparameter changes, some training loop changes, and also some architectural changes. I will not go into detail about all of them, but I will show you the architectural changes in here. So on the top, we have the original architecture. This is the nanoTabPFN that I talked about before, but instantiated with 6 layers. And here at the bottom, we have the final architecture of the speedrun. And I will go from left to right, mentioning the differences. The first one is in the feature encoder. In the original one, we just embedded every single cell independently. In the result of the speedrun, we actually do this feature grouping that I mentioned before. But unlike TabPFN v2, we don't group 2 cells together, but instead we group 5 cells together, and we do this in a repeated manner. So one cell occurs in not only one embedding, but multiple embeddings. This was inspired by Tabical, the repeated part. Now, after this, we have our embeddings, and then we append some thinking rows to these embeddings. They essentially act as attention sinks. And then we apply a residual decay to the activations, where we decay it exponentially the deeper we go. Inside the architecture, we changed layer norms to RMS norms. And then we had one change in the end, which was quite interesting. My student discovered that through running auto research from Andrew Karpathy. And there it's the case that we don't take the embeddings of Y test and give this to the decoder, but instead we take the mean of the embeddings of X test and give these to the decoder. Now, one natural question that comes up is, what if you continue pre-training? Maybe we would optimize for getting to random forest performance fast at the expense of not being able to surpass it. But as you can see here, we're actually able to surpass it by a few more percentage points in terms of average work. Now, high-level summary, we got 81 times faster with 22 times less pre-training data. The repository is here. If you search for speedrunning tabular foundation models or modded nanoTabPFN, you can find it. And of course, my student would be happy if someone of you is interested in trying and beating the current record of the speedrun. So next, we have a workshop paper about evaluating data priors for tabular foundation models. This was also by two students of mine, Zeynep Türkmen and Kürşat Kaya. And here the idea is that priors are important for tabular foundation models, but they are not often like evaluated independently. For example, Typical releases the architecture together with their prior. TabPFN v1 has its own architecture and its own prior, and people don't really evaluate Typical on the TabPFN v1 architecture, on the TabPFN v1 prior, or the other way around. And so we wanted to kind of isolate the impact of the prior and do some analysis. How similar are the priors that we see around? And can we maybe see that priors that generate similar looking data also cause similar looking downstream performance? In order to do this, my students collected a bunch of public priors and created a unified interface for those. Then they also added two priors of their own based on real-world data. One of them by using the original target column of the dataset, and the other one by randomly sampling the target column. This is inspired by TabDBT, which is another tabular foundation model. And yeah, once they had collected all the priors, they went and generated 250,000 datasets of each prior. And then they looked at two things. The first is characteristics of the data, where they essentially computed a vector of meta features that they decided on. And the second is the downstream performance of how does nanoTabPFN perform after training on data from that prior. And once they had this, they could take a look at what priors are similar, what priors cause similar downstream performance. Can you maybe see that data similarity implies downstream performance similarity? And yeah, we evaluated on Tabarina again, and we could already see here that on some data sets, the choice of the prior matters much more and causes a much bigger difference in between priors in the downstream performance than on some other data sets, where all priors are roughly similar. So when we look at the similarity in terms of the data on the left or the performance on the right, we can see that for a lot of these prior implementations, the library that they are implemented in actually has a bigger impact of whether the data looks similar than the actual data generating mechanism. For example, Typical's MLP prior, as you can see here, looked more similar to Typical's tree prior than it looked to TabPFN's MLP prior, which is quite interesting. But this could also, of course, be caused by the specific configuration that we used. And we can also see, when we look at the performance similarity, that some priors, which look similar in this meta feature vector, look very different in the downstream performance. For example, the real data priors, it apparently matters a lot, whether you use the original target or whether you take a target at random. Or we can also see that Typical's tree prior actually has very bad performance, even though it looked somewhat similar to like the MLP prior. Now, the next work is by Ole Ossen, and this was about doing Bayesian tabular feature learning with causal information. The high-level idea is that we have our tabular dataset, and maybe we have some extra belief about how the graph that generated the data or that's underlying the data looked like. Maybe we know that whatever value feature x1 has implies a certain value for feature x2, or that they are independent of each other. And so he looked into encoding information that we encode in form of a graph and giving this as additional info to nanoTabPFN and looking whether this helps in terms of the downstream performance. And the result is kind of as expected, that if we have fewer data points, this helps more, and the more data points we have, the less it helps. Because the more data points we have, the more statistical reasoning TabPFN can do, and the less we need to rely on the graph information. Then we have FairOp-PFN. This is by Enes Hassani. Here the idea is that we have certain kinds of data sets where we consider some attributes as protected. In this example, we consider race and sex as protected attributes. And when you want to, for example, predict the college GPA, the LSAT score, or the first year law grade, we want this prediction to essentially solely depend on the law knowledge of the corresponding person and be independent of these protected attributes. But we can't just like remove these features because there might be some causal relationship between the protected attributes and other features. And so they might have some influence in there. And yeah, well, how do you deal with this? So FairPFN, which was based on TabPFN, not nanoTabPFN, had a method where they generated the data from SCM for pre-training. But then when it comes to generating y-test, the ground truth, against which we train, he went and removed the connections of the protected attribute to the rest of the SCM, and then propagated the values throughout the graph in order to get the new cleaned up label. And then we essentially trained with the signal against this cleaned up label. Now, this is one way to do this, but they had the idea that this might not be the optimal way to handle this by just removing the connections. And so they tried a new pre-training strategy. And this new pre-training strategy, they compared on the nanoTabPFN architecture. Here, the idea is that we still do it like before. We have our SCM, we generate the training part and the features of the test part. But then for the labels of the test part, what you do instead is you essentially calculate the expected value. So let's, for example, assume that the protected attribute is a categorical that can be 0 or 1. Then you would set it to 1 and propagate information throughout the graph and look what the result for the label is. Then afterwards, you would set it to 0, propagate information to the graph, look at the result for the label, and then you can compute the expected value of the label, threshold this since we do binary classification, and this would give you the actual target that you should pre-train against to be optimal for the fairness. Now, the last of the works from our lab that has already been accepted is SurfPFN, which is about survival predictions. Here, the idea is that there's a kind of event that's of interest for us. For example, the kidney failure. And in our table, we have a time when this event will happen, or whether this event, we have a time for whether this event has happened or not, and we have an indicator, which is like a Boolean value for did this event happen at that certain point of time. And so you can see here, for example, the kidney failure that we're interested in, this happened after 4 months. So the indicator is 1, this actually happened, and the time is 4 months. Now, with another data point, another human, and he died of cancer after 3 months. So there was a time recorded, which was 3 months, but the indicator value is 0, since we care about the event of kidney failure, and this was cancer, not kidney failure. So this value is 0, and then we can imagine that we have another patient. There we also have this time variable, and this, but they live healthy, so the indicator is 0, and the time is the current time after diagnosis. And so the idea is that the target that we want to predict, which is the time here, is right-censored. So a lower bound is observed. And if you want to do this, you could think of just doing like regression on this time column, that you filter out all the data points where the indicator says this hasn't happened yet, and we just look at the others and do normal regression. But if we do this, we throw away some extra information, which we could potentially leverage to improve our results. And so he worked on integrating this by handling the right censoring in an extension of nanoTabPFN. Now, the 2 last works that I will mention are scaling laws for nanoTabPFN. That's something Johannes Hoog, my co-author on the paper of nanoTabPFN, is working on, and then the TFM playground. So scaling laws, you probably already heard about them before. People often do this in the LM world, where they pre-train like smaller versions of the model. And then once you have multiple versions and you have recorded their performance and how much compute you needed for these and how much data you trained on, you can go and you can essentially forecast, if I try and train like a much bigger model, what kind of performance can I expect then? And you can also use this to compute what would be the optimal like number of parameters to choose for the data I have, or how much data should I use in order to optimally train this for a certain kind of architecture. And so he is looking into doing this, what people often did for LMs for tabular foundation models. Now, what's different between tabular foundation models and LMs? Well, in LMs, the normal unit for the data is the token, and in tabular foundation models, it's the number of cells in the table. And the search space looks a bit different. We also have model width and model depth, as well as some training hyperparameters, but we also have, for example, features of the prior. For example, the number of features in the data we generate, the number of data points, or potentially some other measurement for the complexity of the data. Now, there was some previous work by Limix, which is not a tabular foundation model, but this has some issues where if you use their scaling laws, they can go out of bounds for the metrics they look at. Like you can, for example, maybe go above 1 in RockOak or below 0 or something. And this is, of course, an issue that he wants to address. And another point he wants to look at is that you can see immersion capabilities in LMs, where for some time you don't see anything, then suddenly it goes up and it can do something new. And this kind of looks like a sigmoid curve. And so he also wants to check whether he can fit some scaling law that kind of looks like that. And yeah, one result he seems to have found so far is that you need to like scale the prior. Previous work like Limix or Mitra didn't do this. And he also varies the number of maximum features and data points inside the prior. And these can be viewed as a complexity, as a proxy for the complexity of the prior. The more features you have, the more potential relations can be inside them, and thus it's harder to understand them. Now, my last point is the TFN Playground. That's another repository we made. It also lives under AutoML, and this is essentially an extension of nanoTabPFN. There we have a more sophisticated training pipeline with some more features, and we are planning to build this out with more tabular foundation model architectures. We have a branch right now in development for adding nanotypical. We are also planning to add nanoTabPFN v3 and probably others like some nano version of TabDBT as well. And we also want to offer priors in there. I'm planning to add some kind of standalone prior implementation in the future. And we already have interfaces to the public priors that we saw before in the prior comparison part in there as well. Now, that's it from work from our lab, extending or building upon nanoTabPFN. Now I want to shout out some work that I saw that cited nanoTabPFN and build upon it. The first one is called Is One Layer Enough? Understanding Inference Dynamics in Tabular Foundation Models by Barlev et al. And there they looked at what do the actual layers inside nanoTabPFN or TabPFN do? And is there maybe some redundancy inside there? And so they also tried some experiment where they just had one layer that they looped. Then the next is shaping the prior. How synthetic task distributions determine tabular foundation model quality. This seemed very similar, coincidentally, to the prior comparison that I mentioned before. It also got accepted at the same workshop. And I think they also fixed the nanoTabPFN architecture and also used the TFN Playground implementation, similar to how my students did it. And then they also analyzed the impact of the prior. Then there's one about latent chain of thought and how this improves structured data transformers. I think this is similar to the idea of coconut in LLMs, where you don't like discretize the output for the next iteration in your chain of thought, but instead you use like the continuous values of the embeddings. Then we had real-time explanations for tabular foundation models. There they looked into creating a version of nanoTabPFN, which also directly outputs the SHAP, the shapely values for feature importance. Then there's in-context multiple instance learning. Here the idea is that you don't have labels for individual data points, but you have labels for bags of data points. And there's actually another somewhat similar paper which also cited us, which looked into in-context positive unlabeled learning. And there the idea is that you have like labels you have positive labels and you have unlabeled. And unlabeled can be either negative or positive. And they also trained a variant of nanoTabPFN extending to this kind of problem. Now that's already it. Thank you for your attention. And here's the repository. Feel free to check it out and maybe also train nanoTabPFN locally on your own computer. Now I'm open to questions.
Okay, thanks, Alex, for this great talk. We really appreciate that. So I think that there were many, I think, interesting points regarding. Also, thanks for the intro to TabPFN and also for the detailed description of your basically uh, first paper and then the follow-ups. It's really great. So maybe, potentially, if no other questions from the audience, I can maybe start, especially regarding this impact of priors on the quality of the tabular models. So especially, maybe if you can go to slide, I think 29, I think around this kind of area, I think we had this
Yeah. Sadly, I
concept.
don't have slide numbers everywhere.
Yeah, I think that.
Yeah, yeah. Right. This was a bit further. Okay.
Yeah, I think this this
Yeah.
this this
Yeah.
uh, this aspect, yes. So I was really curious, so because we have the um, prior, so basically TabPFN version 1 actually released the prior, right? Like synthesizing the data is basically the code actually is in the GitHub. And then we didn't have the code for TabPFN version 2, 3, right? And so I was really wondering, like, to what extent really these priors that you basically find they influence the quality of the models, especially, for example, if we talk about Tabarina, right? So
Mhm.
how we can really like think about how to really find priors, but at the same time, we don't, for example, contaminate these models. So of course, we have this big issue with LLMs that they perform very well on many benchmarks, MMLU, and so on and so forth. And then it occurs that many of them actually were basically trained either on like test set or training set of these benchmarks, or even in some extent they basically like rephrased or regenerated some of this data from the benchmarks, and then of course they also perform well on the benchmarks. So how do you see this kind of issues with TabPFN?
Yeah, so if you use some kind of real data-based prior, where you, for example, augment on real data, I think TabDBT did this, and this can be an issue with like leakage. But if you use like these synthetic priors, I don't think you need to worry about leakage. It's like unlikely that you would find some like method that you would be able to nicely engineer a general method which is still general enough, but somehow specific enough to like help you on this kind of subset of data. I think when it comes to like the priors, what you want to do is you want to try and find a method that can generate like as arbitrary as possible
Mm,
relations inside the data. And the MLP priors and the SCM priors are like nice examples, but you can think about like what might be unlikely to occur. For example, if you use some SCM or some MLP, and then try and think of something that you can add in order to improve this. For example, MLPs are more smooth, and so maybe you would want some prior that generates like harder decision boundaries, like you know from trees. And this is what TabPFN kind of looked into to like use trees for prior. And you could imagine then if you mix these, that this can
mhm,
potentially improve performance.
Can you
So
go
I would,
slide back? Yeah, I think
yeah,
there's also yeah.
slide back.
Uh, I think
It,
that okay. Is it this one? I think okay. Maybe okay. Slide back like 29 and before. Was there something? Uh, oh no. Okay.
it was
I
in the
think
prior
that.
comparison, right? Yeah.
Yeah, I think so. Yeah. Okay. Oh yeah. I think this is actually very interesting. Exactly. Yes. This kind of aspect that still some priors affect quite strongly the performance on the downstream tasks datasets from Tabarina, right?
Mhm.
Um, so choosing some priors might just help to perform well on Tabarina, right?
Yeah.
Which is
I
kind of
think,
interesting. Yeah.
yeah, I think that the prior is like a big part, and that's also, of course, the competitive advantage that prior labs
Right.
keeps it in some way, that they don't release
Mm,
the prior. And yeah,
mm-hmm.
it's probably quite a powerful one that like captures a bigger space than the other ones. And
Mm-hmm.
yeah,
Mm-hmm.
like our hope
Mm-hmm.
here was also in some way that maybe if we can demonstrate that different priors are better on different kind of data sets, this could be a nice
Mm-hmm.
motivation for going and mixing them in some way.
Mm-hmm.
Hope that this
Makes
like,
sense.
yeah.
Mm-hmm. Mm-hmm. And also, how do you feel about kids? So we kind of observed that with, I think that with new versions of the models, you have kind of more priors, or even like more data being generated. So it's kind of also maybe hints to the scaling laws. So basically, is it the case really that, okay, if we have more priors or more generated data from the priors, is it also increasing the performance of the models? Did you investigate more this aspect of scaling laws in terms of priors?
Um, Yeah, like in the scaling loss, he is looking at, I think, all three things, the complexity of the data you train on, like the number of features, the number
Mm,
of data points,
mm,
but also the number of cells, which is like number of features
mm,
times data points times how many tables you have. And I
mhm,
think, yeah, like if you have much more like data, you're likely improving. Now, you could also imagine that if some prior is like more broader and can generate more kind of data, then you might need to train longer in order
mm,
to capture this whole space. Whereas if one prior is like only
mm,
generating a subset of another one, you might not need to train that long in order
mm,
to go there.
mhm,
And of
mhm,
course, it could happen that like one kind of prior looks causes the predictions to look somewhat more similar or more different to one kind
mm,
of data set downstream.
mhm,
And so one prior can have an advantage on one side and a downside on the other side.
mhm, mhm. Yeah, I find it really interesting. It's pretty cool in the sense that indeed, like in this dimension, meaning like the data which is used for training for the LLMs, we have kind of easy kind of job because we just count number of tokens, right? And here is kind of a bit more complex how to really capture this complexity of the data. And as you said, should it be more priors or maybe one complex prior with more data? I think it's a kind of interesting dimensions to, okay, kind of opens this new dimension
Yeah.
also on the level of the input data to the models. Pretty cool.
And even
Okay.
inside a single prior, it can be the case that like number of features and data points is like a simple proxy for the
Mm,
complexity. But if we look at, for example, SCM prior specifically, you could also imagine that the number of edges or something inside this
mm,
graph can also be another
yeah,
indicator. And in
yeah,
tree
yeah,
price, it's another kind of
yeah.
indicator.
Yeah, I was also kind of wondering, so like when you even like okay, I don't know if you kind of invent new priors, for example, like how do you really find the, for example, like weights for the edges in SCM? Like is it something also that you optimize for?
I haven't looked in detail into the priors in working on one myself. I started doing this a little for the MLP prior for the TFM
Mm,
playground. But from my understanding, you just essentially do sample from a normal distribution usually.
okay, okay.
You like you I think many implementations have like some hyperparameters where you randomly decide should I now sample from a normal distribution or from a uniform
Mm,
distribution. Like there
mm,
are many
I see.
hyperparameters for these priors, and then you sample the hyperparameters, and then based
Mm,
on these hyperparameters, you sample the actual rest.
I see.
Like
I
with
see.
an MLP prior, it can be the case that maybe for this specific MLP, I will have another set of activation functions. And for this MLP, I will sample another subset of activation functions of all the ones available.
Mm, mm-hmm, mm-hmm,
But
mm-hmm.
it's
Pretty cool.
basically just
Yeah.
randomly generating the weighting.
Mm-hmm, mm-hmm. I see. Also gonna give maybe some space to other people. Anybody from okay.
You would have to mute yourself probably, so that we don't have an echo. So my question is actually a very concrete one. You were mentioning these thinking rows. Could you maybe explain more what they are?
So this change was introduced by TabPFN 2.6. Like they also did this in the LM build before, but TabPFN 2.6 added this, and so my student also tried this here. And I think the idea is that they act as attention sinks. So maybe you don't want to attend to other things and you want to attend, you want somewhere where you can put like the value of your attention so that you don't care about the other values that much. And so you add them so that if the other values are not that important, you're not forced to attend to them. You can instead attend to the thinking rows instead.
Okay, that makes sense. Thank you so much. Is there somebody from the meeting room with a question?
looking at the question from the Google Doc, I think most of them have been answered during the presentation. Yeah.
I had actually one more question in the sense, like I think it builds up on what Adam said in terms of the priors. So I'm still not 100% convinced that basically like just choosing the buy like it seems like it can be some way of hacking basically the system if you basically just optimize your priors to the tab arena, for example, then it seems like basically a form of benchmarking to me. Like how do you see that?
Well, like, okay, I think theoretically it's of course possible that you can go and you can set up some loop or something which optimizes the hyperparameters of the prior with like Tab Arena as the validation that you look at. This would be possible. Now, in some way, like if you do this, this could maybe be more easily detected if you look then at suddenly, like if you have a very general prior that's very good, and then you look at Tab Arena specifically, and you also look at another kind of data set or list of data sets, if they optimized for one specific, like if it's the case that they are much better on Tab Arena, but you can then maybe look at another set of data sets and there they're much worse, whereas the other one is consistently better on both, this would be an indication that potentially, if they're much better there, but much worse on the other ones, that this would be like some issue there. But yeah, I think in practice, you can't easily rule that out. You can maybe try some techniques which sound similar to the competition you guys were proposing, or like checking was this kind of data set pre-trained on that, like something akin to, I know, some membership inference attack, but for actually like pre-training and not just inference there. But I think this is not an easy task to do, and it would be possible to optimize in a way, but it's of course like hard to tell. And if the priors are public, then it would be rather easy to like check that they are very general and not weirdly hyper optimized for a specific setting. But if the priors are private, that's of course hard to check.
Awesome. Thank you so much for your take on that.
Also, do you have any idea on how the exposing the model to real data in the pre-training process would be? For instance, you could like fine-tune a synthetically trained model with real data, or you could have like a certain portion of the training data real during the pre-training process, and would it? I would like expect it to be better, and also in Tab Arena, you see that there's real TabPFN 2.5, which is quite good. But then again, there's TabPFN version 2.6 and 3, which I think is purely synthetic. They don't use real data. So how do you see the effect of using real data or using it not fully, just like some portion? Would it be strictly better, or would it just purely synthetic, just cover it all?
There is the paper, Real TabPFN, which you can look up, and they originally applied this to TabPFN v2. And there essentially they did continuous pre-training / fine-tuning. They like took the synthetically trained one, and then they optimized it on a curation of I think 70 or so real data sets. And they also tied the weights to the original synthetically pre-trained generated weights. Sorry, synthetically generated and then pre-trained weights. And by doing this, it's like a very brittle thing when you try to fine-tune TabPFN, but they were able to do this and to show that like doing a bit of continuous pre-training on real-world data slightly improves the performance. This did do it for V2. It also did do it for 2.5. And my guess would be that it probably also helps a little on 2.6 and 3, but that they still haven't done that like yet. Like I would imagine that the priors are very good and very general, and you can see that even the like non-fine-tuned ones are dominating all the other methods. But I would assume that if you add another slight fine-tuning on real-world data, this should be able to squeeze out a bit more performance. And TabDBT in here, which is also potentially interesting for you, was pre-trained just on like real-world data by doing a bunch of like augmentations inside of the tasks. And you can also see that this is beating the traditional methods that we had in the past as well. But yeah, in short, adding like continuous speed running or fine-tuning on top should be able to squeeze out some performance. And I know of a student at my lab who is also looking into mixing like synthetic data and real data during pre-training. But he's looking into this especially for like context tab, which is an architecture, also Table Foundation model, which handles this year got renamed to SAP RPT OSS, which handles semantic meaning as well. And yeah, they're doing some exploration in that regard, but fine-tuning on real world data is still helping right now.
Thank you.
But one point that might also be good to point out is that, like, if you want to purely pre-train on real-world data, this might be hard since there's not like high-quality real-world data to train on, not a lot. Many use like T4, which is like a web scrape with a bunch of like millions of tables there, but some of them are not like high-quality tables to pre-train on. Or you could also imagine that there are some tables on Wikipedia which don't constitute a predictive task. And so the lack of large amounts of high quality data for pre-training, as well as potentially some licensing issues if you pre-train on real world data, could be another couple reasons why people might not like look into this that much and more focus on like synthetic data.
Thank you.
Maybe in the meantime, there's some still questions. So basically, I think it kind of maybe here, if a company like SAP would train these models internally on their own large number of tables, which I suppose are also of high quality, this might actually basically give a high quality model. So actually, in this case, I think that probably for, let's say, us researchers, it's more about finding architecture, or as you also said, many of these kind of tricks, insights, how to really design a model that can really perform well on any data, and actually then the data actually would probably be uh, finally, like once you have the architecture which is optimized, the major factor. So then companies who have internally potentially many banks or SAP or such companies, they actually could internally have a very high quality model.
Yeah,
Any
I
other
mean,
question? Yeah.
if you have like a lot of data sets from one domain, maybe this could also give you a model that's good for that specific domain, right?
Right.
But then maybe you'd have an issue if you want to generalize to other domains in some way.
Correct. Are there any maybe last questions from the seminar room?
Francis's question kind of already covered this, but I assume for the speed run it works with the subset of the data which you use to train. Does it work for any random 14,000, or did that optimize to some 14,000 which just are better examples for teaching?
What do you mean with 14,000?
For your TabPFN speed run, I think that was one of the first papers.
Yeah, this was here.
Yes. Oh wait, it wasn't 14,000, it was 3,000. Okay, I just misremembered the number. Sorry, but yeah, does it work like if you pick those 3,600 data sets randomly, or are those optimized as well?
So in the speed run, my student generated 250,000 of data sets using the typical prior with like certain limit for the number of data points, number of features. And he just used this throughout the speed run. He did not like optimize the data sets in any way. But it would have been allowed to pick them in a certain way. And one could also imagine that like some kind of, for example, curriculum learning could help, where you try and like change the kind of data over time, where you have simpler data sets from a simpler prior in the beginning and then increase them over time. Maybe this could also speed up the pre-training, but we didn't do anything like that. We just had a fixed prior dump, and then we just needed less and less data because of changes in the architecture training loop, not the prior.
Okay, interesting.
But I'm actually supervising a group of students here that are looking into like curriculum learning for nanoTabPFN and whether this can like speed up the training there. Not in the speedrun benchmark setting, but in their own.
I mean, have to be careful to what extent you take it, because at some point you could just be taking a similarity metric and just finding the data sets which are most similar to the target, and obviously that would be then probably declassified as cheating.
Yeah, like you're not allowed to load any pre-trained weights. You're not allowed to just take the targets and immediately overfit on those. Like we would have to have some limitation in there. We couldn't allow like anyone to submit anything on any data. We would have to actually check this in more detail than if someone like starts and does like prior changes in the speed run. But there's actually some related work in Typical, if you are interested. There they went and they did a very simple form of curriculum learning where they trained in like 3 different stages over time. But I think this was not like really scientifically looked at in detail, and more like it just happened to be like that.
Sorry, one last question. You mentioned that real data sets for tabular data are noisy, for instance, T4, but you still have to evaluate on them. So do you just ignore them for now, or do these papers do some kind of cleaning on the T4s to report the evaluation numbers?
Well, there's a difference of like real tabular tasks and not real tabular tasks. Like we benchmark on datasets which are curated for being like actual tabular tasks and not like random tables or something. But when you go and you like do web scrape in order to get millions of tabular datasets, you might get like some tables from Wikipedia, for example. They're like, you could imagine there's the football player, the name, and then the number on his shirt on the back or something. And there's no predictive task there, right? You can't use the name in order to predict like what number he will have. Whereas if you have like some medical data set, there would be a predictive task there in there probably. And so the benchmarks, they actually curate for being proper predictive tasks. Especially TAP Arena has a large section about which rules they use to filter out data sets and how they curate it. Whereas if you just like do web scrapes, something like T4, this does not apply such strict rules in order to filter out such data sets. There are of course some rules, but it's not like that strict of a setting. So I wouldn't go and evaluate on T4. I wouldn't do that.
Okay, I think that also we are at kind of 1 hour time. So again, thanks a lot, Alex, for the excellent talk and answering all of our questions. Really appreciate that. And probably can just stop recording for now. Yeah.